Okay, so I will start with a short introduction of DEKEMA itself, before I start to go into detail on sintering furnaces and what we think makes the difference. Now, DEKEMA itself is a company which had been built up around 1973, but before this guy, does it work? Okay. This guy, Mr. Hindenburger, already invented the first vacuum furnaces. So he was the one in the 40s who thought that vacuum might be very good for ceramics. He was a dentist, but went more and more and more into all these ceramic applications. He even was at the university in Chicago in the 30s. We've got a patent on that from 1936, which saved us quite well regarding some competitors. That's why we have a mechanical pressing system. Only we and the other one. Yeah, so he constructed furnaces more or less for everybody in the 50s. Then he wanted to even invent his own ceramic and founded, Then for the furnaces, he created the company Dentalofenbau, which means nothing else than building furnaces, dental furnaces in the 60s. Yeah, so we had the Panama furnace first from Dr. Hindenburger, and with this he wanted to sell dental-keramische Massen, dental ceramic masses, and this is where the name comes from. That's why they're called DEKEMA. This didn't work so well. This company, which was founded in Frankfurt, moved to Freilassing, which is just nearby Salzburg on the Austrian border, and he switched the name to Dental Ceramic Machines. And with this company, we built the 2001A, the Ostromat 2001A. That's, by the way, why it's called Ostromat, because it was an Austrian with an Austrian company who was now building furnaces in Germany and wanted to stay with the Austrian name, so he called it Ostromat. And maybe you know about the Ostromat 2001A. This was a furnace which was sold in thousands by Vita. So there was a strong cooperation between DEKEMA and Vita at that time. Dr. Rauter and Dr. Hindenburger understood quite well, and Vita was selling this furnace more or less worldwide, and from Germany, on the Austrian border, from Austria, these furnaces were sold only locally by DEKEMA. But still, we use the same name because through Vita, the Austrian mark name was spread worldwide. Okay, so that's about me. Basically, what's standing there is I'm not a dentist, I'm not a dental technician, I'm a physicist. I got introduced into DEKEMA already in the beginning of the 80s. Lots of information from my friend's father, which was Dr. Hindenburger, and I always liked this company. I saw that this is a niche where you can reach quite a lot and where you can approach, with all the knowledge you can approach ceramics and this technology quite well. So finally I started in 2003, which is now 21 years with DEKEMA as a CEO. Yeah, and that's where we are now. Okay. We're about 40 people. Don't forget we are in Germany, so we only have 33 pictures. Some people don't like to have the pictures in. That's how it is. Even downstairs I was asked whether they may use my QR code because I'm German. Yeah. Different digital laws. Yeah, this is where you see, this is where we are located. Yeah, it's just at the border to Austria. This is where many companies in the 70s moved because Austria was not part of the European community, and these companies all wanted to put their products into the European market, so they just switched to the border and cooperated with the Austrian mother companies. And there are a lot around, so you have, this is the mecca of dental here in this area, Liechtenstein, Pforzheim, Stuttgart, Karlsruhe, here, and then we have Frankfurt, just to have a short view. Okay, so all products are made in Germany. That's how it is and how it will be. DEKEMA won't produce anywhere else. We are absolutely proud that most of our parts are from local areas, from Germany, and yeah, and this is where the quality comes from. Okay, so just a short movie to get a little more insight.
Big within small, with passion and dedication to detail, and perfection and precision overall. At DEKEMA we have been developing and manufacturing furnaces for the dental industry for over 50 years, from our manufactory in Freilassing to the whole world. Our aim? To create a precise tool that will accompany dental technicians throughout their entire working lives. Like many big things, everything began with just the first little step. It all started in 1973 with the Upcera 2001. Durable and highly precise, it revolutionized the dental market. A product 100% made in Germany, manufactured regionally right from the beginning. Always with a vision, we were the first company in the dental industry to rely on digital networking and brought the Internet of Things into the dental lab. Today, around 40 colleagues and perfectly trained teams provide global support at all times. In this process, we rely on our decades of experience. We have constantly expanded and further developed proven technology. Our DEKEMA firing chamber, designed decades ago, used for decades, refined over decades. This is how our products have always been creating the dental lab of tomorrow. We take efficiency and precision to a new level. With our experience in the digitization of analog processes used worldwide, we create a unique workflow that brings the analog and digital worlds together in one 3D printing process, the TRIX process. Our DEKEMA Circle Cloud functionality connects the work processes seamlessly. 3, 2, 1. Industries ask to use our tools. They are approaching us looking to participate in our precision, connectivity, and lead in technology. The development of new products and the continuous further development of our software is a matter of course for us. Where the design of the perfect furnace was created by hand in the past, we today rely on fully digital processes. We simulate the visualization of individual components with augmented reality. This allows you to place your desired product virtually in your working space. Integrated into fully automated process chains, you produce high-end products with DEKEMA. For operations of any kind, from the small lab to the largest industry.
Big within small.
That is fundamentally the standard of DEKEMA. The quality of a small series production, this flexibility and dynamism of a small manufactory, combined with the reliability and professionalism of a large company. In small teams, we work all the closer together. My colleagues, my friends in this company are fantastic. Awesome. I am proud to be a part of this team. Personal exchange, focused discussions, pros and cons, trial and error, all in the interest of the company. The product management, the administration, my colleagues in the other departments, research and development, production and manufacturing, sales and marketing, purchasing, service and IT. We all ride the same wave. Together, we're surfing confidently into the future.
Nice area. Yeah. We work where many other people want to make holidays. The southern part of Germany, that's really nice. Salzburg Festival, really nice. Okay, so now we are getting serious. Austrian Sinter, high temperature technology. What's it all about? Basically, we started with this concept already in 2007 when we introduced the Austrian Music, which we are still manufacturing in small quantities, but we are still manufacturing this furnace now, 17 years ago. With this furnace, we even started with memorizing data, so 100 cycles stored inside the furnace, having all information, all parameterization, just to know what's really going on. And the current series, which is Series 6, which we also have private labeled as an Upcera furnace. So the Series 6.4 with a small chamber and the large chamber of the 6.7 for 10 centimeter discs. And the Series I, our IoT furnaces, which are completely IoT functional, communicating in between each other with our server, with our cloud. So, what's this all about? So sure, basically, as I said before, I was impressed even 30 years ago how you can handmade this quality when you focus on one thing, on the furnaces for ceramics. We're having all this information, always trying to be on top for many, many years, which is not easy at all, I can tell you. It's really not easy at all to keep standards, like with the 2001A at that time, or the 3001, which many people surely still know, which was a furnace fully flexible, programmable, more or less not usable for many dental technicians because the language was quite complicated, but you could program whatever you want. And this gave the possibility at that time for low temperature ceramics, low fusing ceramics, because you needed completely different vacuum and drying times at that time. And then surely all these, the sintering, this technology where we go into detail now with a controlled accuracy of 0.25 centigrades at 1500 degrees. Why do we need this? What does this mean? What do I say if I talk about no discoloration? That's what we would see. Then the live stream, so having programs available. We want to have the flexibility of a 3001 of this furnace language in all furnaces, because we want you to be able to program whatever you want. So to give you this possibility without programming yourself, we created a database during the last 24 years where we put all the programs in, where ceramic manufacturers, even big competitors, come to us, give us the programs to provide it for this database. And you can directly download it, you don't have to program yourself. And as I said before, the IoT cloud functionality, which even gives us more possibilities, where we know before you know what's going on with your furnace. It's really difficult to understand that what you think you see and what's really going on are two completely different worlds. And this is what, as a physicist, you learn as a main topic. The devil's in detail, old Marco. Okay. So we will talk about thermocouples. We will talk about heating elements and sintering means, sintering rings, plates, crucibles, whatever you do. Why do we use different tools for that? What's the difference between a DEKEMA and other devices? Yeah, never forget, a device, a product can only be as good as the worst part inside. As soon as you try to reduce costs, as soon as you try to put something in which is not as accurate as the rest, you don't need the rest. So you have to be up to date, you have to be the quality with every single part, whether it's an insulation, whether it's thermocouples, heating, and whatever it is. If you try to reduce these costs, you destroy the furnace and destroy the quality. This is a catch-22 because surely we want to spread our furnaces, we want to make them more cost-effective, but we won't make them cheap. Because then, it's not a DEKEMA anymore. Thermocouple. So as I said before, what you see here is one of the data of the information we get from every single cycle. So with the Series 6 furnace, that's stored inside the furnace. With a backup, we get it into the database. With a Series I furnace, the furnace even sends us the data to have it already stored inside our database. In this case, you see, let me check, you see the power consumption, you see the lift movement, you see the temperature as it is and as it should be, actual and destination temperatures. And now we move up with the temperature to somewhere, 1500 degrees, or 1560 in this case, 1560 degrees, and we open this, and you hardly see any deviation. That's controlled accuracy. And you can check this with every furnace. This is a data file which everybody can look into. That's open. This is not something, how do you say in English? It's data massage. This is real. And how can you reach that? In the current stage, the final stage, we have a thermocouple. So the temperature measurement with this pin here, which looks directly into the chamber. We don't want the thermocouple to have sunglasses for the radiation. In every other furnace, you have a so-called encapsulated thermocouple. So you have a closed rod, and inside there's this thermocouple wire. What is happening in this case? In this case, as I said, it's like sunglasses. You are not looking directly into the temperature, into the radiation you want to see. The temperature always has to go through this alumina rod. And not only that, it's not only the temperature which is going through, it's even the pollution inside. You have lots of pollution. You have pollution through the zirconia, through the coloration, through acids, not with us, but even through heating elements. And this is accumulating on this alumina part, leading to a permanent temperature change. And this is what we want to diminish, what we want to hinder, negligible pollution. How do we do that? As I said, it's patented. First of all, like all DEKEMA furnaces, the thermocouple sees the real radiation. Just imagine you have a fast sintering cycle. You want to sinter like with some materials. You're going up. You have a 24-minute cycle with a DEKEMA furnace, and rising temperature. You start at 1,000 degrees. You go up with about 100 degrees per minute. Stay for 10 minutes, 8 to 10 minutes, and then you just cool down. With this temperature rise, you must not be go over the peak. Yeah, you have to have a real flat curve with the temperature. You don't stress the zirconia material. Even more stress the zirconia, which you already stressed through the short cycle. With this technique, we have an absolutely instant redundance between the thermocouple and the controller. Here, the temperature outside and inside, maybe you have a 2 seconds delay. So how should you control that? How should you control that correctly? You can't. But still, if you have an open thermocouple, and this was what we also learned with the first music furnaces, with this old, huge ship, these thermocouples were eaten up by the pollution inside the furnace. Especially acids from the coloration liquids are a real issue for any furnace. But in these cases, maybe after 200 cycles, the thermocouple was eaten up, it was completely etched. So now we have what we call what is more or less crucifying cathode, meaning there's a platinum part on top which is covering the complete thermocouple and which is accumulating the pollution, but it's not going into the thermocouple. Here, you more or less get a complete doping of the thermocouple, which is leading through a temperature shift, through a measured temperature shift. So only this technique guarantees the unbelievable accuracy of the thermocouple and really an accuracy using fast sintering cycles. Fortunately, it's patented. There, break something. So this is how we put it in. That's why we only have a limited height. Normally it's a little higher, so we have a limited height for 2 to 3 stages, depending on the furnace. And here we measure the real temperature, the real radiation inside the furnace. Don't forget the picture with the other thermocouple. You have at least you have something like sunglasses. You never see the temperature, you never see the radiation which is really inside the furnace. By the way, you won't believe what's going on in the furnace at 1500 degrees. This is like heaven. Everything is ionized. There's life inside. Now we go to silicon carbide. Basically, there are 2 techniques. Some people talk about 3, but the third technique is something like SiC technique. Induction furnaces do nothing else than a SiC heating element, using SiC or molybdenum disilicide. So when I was, that's also 1994, I made my diploma thesis in semiconductor physics. And I was working with a company called Wacker. And Wacker is producing silicon wafers. They have to anneal these wafers. As you know, wafers have to be absolutely clean. They must not be doped at all. And how do they clean that? They take the silicon material and move it out of the crucible with silicon carbide heating elements around, because they don't pollute the silicon. And this was when I started with DEKEMA, and we said, oh, what can we do? We should make pressing furnaces, not just firing furnaces, and sintering is also quite interesting. Everything which needs accuracy in ceramic. Maybe we should look into SiC technology. But controlling this stuff, it's a completely different thing. So SiC is clean. Moses pest, in my words. Why? Again, SiC elements have an inert cleanness. And if you heat with SiC, the SiC element cannot accumulate pollution. MOSI is exactly the difference. With a MOSI element, you always have a glass layer around which saves you from pollution. Because inside this MOSI element, you always have inert accumulation of different rare earths, of different polluting, greening, discoloring materials. And these glass layers reduce. There's even an area, this is not from me, it's what they call it, pest oxidation. There's an area where it extremely accumulates all the pollution which is around, and then it spreads it again at high temperatures. And as soon as the glass layer is gone, because it's reducing permanently, it's distributed into CO2, carbon dioxide, and into glass. CO2 and so it's a gas out. When this layer is gone, you have a lot of spread, and this is what you know from your zirconia. As soon as it gets yellow or green, this is not coming from the zirconia. Maximum operation temperature, 1600 degrees. This is what many people talk about. Yeah, silicon carbide is nice material, but you cannot really heat that to high levels. And you're always squeezing out to the limits. That's why they are not so robust. No, it's different. You cannot compare this with MOSI. Yeah? The maximum temperature, which you're always told with a MOSI element, gives you the dissolving temperature of this element. It doesn't tell you which temperature you really heat it. It just gives you an idea whether it's the longevity is longer till the glass layer is gone or not. So you cannot really compare the operating temperature of a SiC element if you do it precisely, if you know what you do during control, and the max temperature of a MOSI element. For me, it's like talking about cars. Yeah? It's like you have an electric car and somebody comes and tells you, but how many cylinders? None. Not a good car. That's a different parameter. No cover of coatings needed. What do I mean? If you don't want to have green or yellow stages of zirconia inside the furnace, you have to put it in a crucible, because then all the pollution cannot approach your zirconia. We don't need to do this. We can directly work with the radiation which is approaching the material. So we have an accurate sintering control, we have temperature control as we saw before, and we don't need purging. Purging cycles with MOSI furnaces is nothing else than recreating a glass layer on the molybdenum disilicide, so you don't have any more greening effects. What you surely should do maybe after 2 months and then weekly, in a 10-hour cycle, because the glass layer has to build up again slowly. How long does it last? Nobody knows. You know it when you have the next green zirconia. Just let technicians get used to it. Oh, it's not the right color, I put whatever color on it. But this is not good, it's not real. Yeah? So no purging cycles needed. No second atmosphere, because if you have a crucible and you close it, it's like with a thermocouple. You're in a house. Here, do we have the same temperature outside when the sun is shining or not? No, not at all, because you have a completely different regime inside. You never know which temperature you have inside. You only know the temperature of the thermocouple. But if the temperature of the thermocouple is exactly the same as your zirconia, you know that's the right temperature. That's why we work in an open regime. We want to know which temperature we have on the zirconia, not inside some crucible. Then the robustness. This was 2008. So we started with 3M and the first music furnaces in the US. And I wanted to convince them that they should use fast cycles. And we had the Doceram materials at that time. Doceram, I can talk about this because the company doesn't exist anymore, not because of the zirconia, they were bought by Dental Direct. And we had a 90-minute sintering cycle with the zirconia from Doceram in 2009. And what we were told by Wieland, by 3M, nobody needs it. They all sinter overnight. No need. Okay. So we couldn't, small DEKEMA couldn't convince anybody that a fast cycle will be necessary. Now everybody talks about zirconia less 1 hour or even less than half an hour. So fast. This material can be stressed. We don't talk about lifetime. We talk about cycles. And this is what you even should do with these. When I talk about a 10-hour cycle, and we currently would suggest to exchange the heating elements every 700 cycles. So we talk about 7,000 hours. Now, as people only, since 10 years, especially in Korea, drive 90-minute cycles with a DEKEMA furnace, this goes down to only 3,000 hours. And it looks like these heating elements are not as strong as MOSI. But it's not about this, it's about this number of cycles which we drive. So please remember, it's about the number of cycles you're running, how often do you heat up the heating element and cool it down, and not about how long you heat it. There's a small difference, and you can imagine from my explanation before that these heating elements build up these glass layers. So surely the longer you reduce it, the less you have a good result, because there's no glass layer anymore. But still, we should talk about cycles, and this is, and then you will see that we talk about completely different longevity with a SiC element and with a MOSI. made in Germany. Let's see. You see the difference. So it's the basic material is DEKEMA specific, made only in Europe and in Japan, and we assemble it. We check it and we assemble it. This is because we need this kind of special recrystallized silicon carbide, which I think nobody else can get. So surely go to Alibaba and you find DEKEMA heating elements for 80 euros. We know what you take, what you put into the furnace. We know how much electricity consumption you have with the furnace. We tell you immediately what you put in. So don't blame us if they don't, if they are not safe. So really, summarizing with the SIG material, if you know what you do, how to control it, and you have the right material, it's a no-brainer. Okay, so summarizing up again. As I told you, I didn't know the slices before, but now it's a summary. Now we can summarize it. It's a characterization temperature, not an operation temperature, what they talk about when they talk about 1800 degrees. And what do you need an 1800 degree heating element for? Zirconia. Discoloration because of rare earth, molybdenum trioxide, and so on. Layer growth, meaning you need glass. Past oxidation of these layers, which lead to a pollution of your zirconia. And cleaning and regeneration cycles, purging cycles, which you need every 1 or 2 weeks. If you don't do it, okay, you have green zirconia. If you want green zirconia, don't buy a DEKEMA. And this is a typical result we got from a customer, not from us. Typical result, not colored white zirconia out of a MOSI furnace. And I think everybody who has a MOSI furnace saw something like that. Whether he knew that it's originated by the heating elements. Crucibles. You see the color of these crucibles. You see the color of these pots. And again, you need a crucible. You close it, you cannot sinter fast. As soon as you work like this and you have high heating rates, this will all explode. Because these parts cannot withstand the high temperature changes, the high temperature. Yeah? That's why we have a patent on rings and plates, as we call them. So we have a horizontal and a vertical part. The ring is a vertical part, and the temperature expansion and shrinkage is fully independent. That's why we heat up so quickly with the right material. This is not aluminum. Yeah. No covering necessary, first of all. So even the rings have huge openings to get the radiation in. And the plates with numbers on one side, so you can put single units inside, with a flat part for, you will see later, for micropearls on the other side. And even if you want to work, I don't know why, with a very thick bed of pearls, you can put them in here and put your zirconia. But why are you working with a thick layer of pearls? To stabilize the zirconia. It's not really stabilizing. It's even worse. Now, where is it? Here it is. Because with a thick layer of micropearls, if you put it in and they shrink the zirconia, you easily get destabilization in between or even in these. What we suggest is using so-called micropearls. We have pearls with a very small deviation, around 0.5 millimeter small, and we only put one microlayer, one layer on this plate, and then the parts on top, because this is like friction-free movement for the zirconia. You have the perfect radiation input. The part can friction-free move on this one layer micropearls, and it's finished. I don't even mind whether you put your large spans like this or like this. Insulation. Okay, yeah. Impact of tray placement. When I come to customers and I realize that they put the first layer of zirconium on the insulation here, I see that they don't know what they do. We try the best insulation for the zirconia to get the best energy input which you can have. And they put the zirconia on the ground. Why do you do that? If you have a marble, you're in a room and you have a marble floor and you're going with your bare feet, it's cold. What do? I use a carpet. You insulate because that's too cold. Or even shoes, you wear shoes, that's even better. Or you use wood because wood is insulating. So it's even nicer to go on a wood floor than on a marble floor with bare feet. Maybe. So you have a completely different view. It's you don't want to get all heat into the insulation. You want it insulated from the ground. And when I hear from somebody having his PTC ring and say, the furnace is 20 degrees too low. I know 20 degrees, you put it on the insulation, not on the plate, on the insulated plate. Because this insulation will squeeze out all the heat of the zirconia, and the zirconia won't see the real temperature. That's why we created the first ring as an insulation to the ground with the first plate, and then you put the zirconia on the first plate. And don't use the ring upside down. Why should you use a ring upside down? This is a patented table. On this table, this is a multiple compound table with alumina rods, which are not going to the ground, because they also have to be insulated. And this ring itself is again insulated from the insulation here, from the table. So even if this wearing part is wearing, it doesn't matter, because the ring is not held by the insulation, it's held by the rods. Nevertheless, with other furnaces, you never remove these parts. Why do you remove the ring from a DEKEMA furnace? Because you don't use the right handling tool. Why do you complain about rings and plates which are breaking? Because you don't use the right handling tools. Come to that later. So, as I told you before, this is how we would like to work. Only one layer of micropearls and the material on top. Okay, let's come to this first. And then I talked about the right tools. If you have the right tools, you don't remove these rings. But most of the people don't bother. You have a metal plate. You use our plate with the zirconia on top. It's hot. Remove it and put it on a metal plate. It's thermal shock for everything. And what you then produce is micro cracks inside the plate, which you don't realize at that moment, which you realize in the next part of one of the further of the subsequent sintering cycles. So you think this plate was breaking during sintering, but basically it was already breaking when you put in the thermal shock. So never put a plate, also with other furnaces, never put it on a metal, metal grill. What we created is a special, we call it cinder place, which is a special insulation stone and one ring. So you use the gripper, and with the gripper you put the plate on this ring, and all these components don't see any temperature shocks. So the rings more or less last forever. So that's all a handling question. Basically, I talk about a lot about these things, but that's what I'm for. You don't have to know this. You should just know, please use cinder plates in the gripper and don't remove it with your hands. This will make your life much easier, your costs much easier, our revenue less because you don't buy some plates. But not so many complaints, and this is also good. Okay. Let's go back, here we were, let's go back here. Additional steps to success. DEKEMA patented a tool which was called AutoDry in 1997. What we did at that time, we wanted to have the furnace already preheated for ceramic furnaces. We wanted to have the furnace already preheated and use the heat of the chamber for drying ceramics, which is a typical temperature of 160 degrees. You can adjust it, but it's typically you work with 160 degrees. And during the heating up of the chamber, we move the lift that way that you really have 160 degrees radiation on this table. So there is a homogeneous radiation coming down to dry your material, and you can right away close the lift after that and start your furnace. This has been expanded to the complete temperature range, even for sintering. So what we now included in all these furnaces is the possibility to work with the residual radiation of the chamber. You don't know, but these furnaces open already at 1,000 degrees. So you can open a DEKEMA sintering furnace at 1,000 degrees. Nothing should happen. You can close it at 1,000 degrees, you can open it, you can use this energy, the residual energy of this chamber, which is very hot, for subsequent cycles. Coming back to MOSI, MOSI is brittle. With a MOSI furnace, even it's fast, you have to wait and cool down less than 200 degrees before you start the next subsequent cycle. So a fast furnace can be quite slow if you have to wait till it's down to 200 degrees. With a DEKEMA furnace, if it's still 600 degrees, 800 degrees, we don't mind. If you want to start a subsequent cycle, the cycle tells you start with room temperature and go up to 700 degrees with 60 centigrades per minute. We will move the lift the way that the zirconia sees 60 grades per minute by moving the lift. So we still have a hot chamber. We move the lift the way that you have your first rising temperature steps, and you can directly proceed. So when I talk about a half an hour cycle, I talk about a subsequent half an hour cycle which you can run 48 times per day. When I talk about 700 cycles for a heating element, this means 2 weeks for a heating element. But not because the heating element is so bad, no, because it's 700 cycles. So this is what you can do with such a furnace. You won't be able to do this with a MOSI. With the right tools, even these elements even these parts will survive. Okay. So, equally exposed to heat, with any temperature up to 1,000 degrees, in any furnace, whether it's a firing furnace or it's a sintering furnace, besides our small 220. So 220 doesn't work with this feature. All the other furnaces have it. We don't need a camera. I don't know why you need a camera. It's a matrix. It's a lot of data. That's a lot of experience. That's a lot of information inside the furnace. I don't like cameras which get dulled only by 20 cycles. You have to remove it or to clean it or to switch it off, whatever. All objects are equally exposed to air, to the heat, because the heat comes from the top. Even heat distribution and no stress for this ceramic restoration. So just remember, auto dry coming from drying ceramics, but basically being able to reproduce any gradient, any heating or cooling gradient on your zirconia. So when you want to cool down with 200 centigrades per minute, and you're below 1000 degrees, the chamber opens the way that the zirconia sees 200 centigrades. Okay. Now, we didn't talk about why do we need such a precise furnace. These stupid over-engineering Germans, sintering furnace with 0.25 degrees. A sintering furnace where we even just created a calibration tool which is helping this furnace to be really calibrated. What do I mean with that? Calibration. In case you calibrate other furnaces, you will realize that the manuals tell you if your PTC ring shows a deviation of more than 10 degrees, you should recalibrate it. If I talk of calibration of more than 10 degrees, you would never have to calibrate a DEKEMA furnace till the thermocouple is broken. But through ISO and customers who want to calibrate, typically once a year, we need to have an easy tool, not too expensive. With the music furnace, we had a calibration with an external thermocouple, which was $2,500, because you needed a special insulation table, you needed a special evaluation electronics, and so on and so on and so on. This is what was sold more or less with to every 3M service engineer. Good for us, but not for the customers, because they couldn't calibrate themselves. So now we found a solution how to calibrate DEKEMA furnaces with PTC rings the right way. What do we do now? You get a caliper from DEKEMA. If you use micro gauge, if you use that, you don't have to calibrate at all, because a micro gauge will give you 10 different values from 10 different dental technicians. That's absolutely inaccurate. You get a micro gauge from DEKEMA, you have a PTC ring, you need to know the right batch number, you need to know where to place it, you need yeah. What do? You take the ring, you put it into the furnace, you use the calibration cycle, you must not use any cycle, nobody knows that. If you don't use something else than 1 hour, you have a deviation on the ring, because the ring sees less or more temperature. So if you put a PTC ring to your standard zirconia cycle, which has 2 hour sintering times, it will give you at least 10 degrees too high temperature, because the ring shrank during the second hour. Nobody knows that. Use a calibration cycle which is already in the furnace. So you use this cycle, you go to the DEKEMA online platform, you give the serial number of the furnace, the batch number of the ring, the diameter of the ring, and you get your CCF. You get the parameter of how you have to change it inside the furnace. And this data automatically stored inside the history of the furnace. You can always look at it. You can use it for your quality management. That's all included, DEKEMA Online. That's all included as soon as you buy a DEKEMA furnace. You need to see rings the right way. So what I'm talking about again, we are now back to zirconia, especially colored zirconia, multi-layer zirconia. The problem with these zirconia is that you always have a trade-off between translucency and color. And you have the right temperature the right temperature edge, which you want to reach to have the right translucency and the right color. If you go higher, you more or less burn the colors. You have less coloration, maybe better translucency. Because translucency, by the way, does nothing else than destroying the grit of zirconia. First generation zirconia was heated up to 1600 degrees to have best translucency. This was done because people wanted to destroy the zirconia to have the best translucency going down. So it's an amorph material, you have different grids inside, different expansion factors. It's a mess for the zirconia, but it's a better translucency. And then you put the color in with the last generation zirconia. So now they realized the highest temperature is not the best. It's always the temperature where I get the best translucency and the best color. And this has to be found. And this is, in any case, this is not more than 1560 degrees. For most materials, it's somewhere around 1450 to 1530. So having the right chrome and having the right translucency gives you a very small temperature range where the furnace really works precisely. And this has to be precise and reproducible, like with a ceramic furnace. And this can only be done if you have the right tools, if you have the right parts, if you have the right materials. And you have the right service in the back through DEKEMA. Okay, so far? Questions? No more questions?
He got off easy.
Yeah, it's always, I didn't know when it comes, but it's more or less always the same.
I'll ask one question. How does the oven compensate for mass?
We don't have to compensate for mass. Why? What do I say? When we have a power, the furnace has an automatic power consumption. From silicon carbide, it's absolutely necessary. In my eyes, other furnaces must not do it because we have the patents on it, but it's absolutely necessary that you have the right balance between power consumption and power and radiation. So when you have more material inside the furnace, the heating element will need more power to heat up, but the control will always limit to the maximum. How should I say? To the limitation of all values you may use. So you will never overstress the furnace or the material or the sintering means or whatever. Yeah? So this is all implemented. So if, in case you work with 80 samples at one time, the furnace will need more power. But in case you need more power, then depending on the furnace, somewhere between 10 and 15 amps, which you can, by the way, which you can set up yourself inside the parameterization, the furnace will not heat up so fast. And when customer comes to me and says, now I have one layer and I have 40 units inside and they want to sinter with 60 centigrades per minute, but it doesn't do it, I tell him, first of all, I wouldn't do it because this will all explode. But secondly, the furnace can't because you have too much power consumption. Yeah, so this is the basic limitation. This is also the limitation for the heating elements, that they don't break. So it's always a redundance of how much mass you need to heat up, because through the mass you have inside the furnace, the heating elements need more energy to heat.